Hey everyone, welcome back. Today we're diving into 3D game physics. Imagine creating a virtual world where objects fall, collide, and interact, just like in real life. By the end of this video, you'll know how to make these realistic physics simulations yourself, and you'll see how adding physics can bring your games to life in ways you never thought possible. So stick around, because you won't want to miss the exciting demos and practical tips we have in store for you. Let's jump right in. We'll start with a simple example, a ball falling and bouncing on the ground. This will help us understand the basics of setting up a physics world and adding objects to it. You'll see how gravity works in a simulated environment and how objects interact with each other. Next, we'll look at a stack of boxes to show how multiple objects can interact via friction and affect each other's movements. You'll learn about collision detection and response, which are crucial for creating believable physics in games. Then, we'll add some interactive controls so you can see how user inputs can manipulate the physics world in real time. This is a key aspect of making your games engaging and dynamic. Then, we'll explore more advanced concepts like constraints and forces, giving you the tools to create more complex and realistic simulations. And finally, we'll drive a car by height-field terrain. By the end of this video, you'll have a solid foundation in 3D game physics and be ready to experiment and create your own interactive worlds. All right, let's dive into our first example and see physics in action. To perform a basic physics simulation, we need to follow these steps. Create a physics world. Add a ground plane. Add a sphere object. Apply global gravity. Let's see this code in action. However, you might notice that nothing seems to be happening. The object isn't moving. This is because we need to continuously calculate how the world and all its objects change over time. By taking delta time as an input parameter for all the physics equations, we can calculate the positions and states of objects for the next frame. This process is repeated frame by frame, allowing us to simulate smooth, natural-feeling physics. As we begin the simulation, gravity takes over, pulling the ball down towards the ground. When the ball hits the ground, it bounces back up, losing a bit of energy with each bounce until it eventually comes to rest. This demonstration will give you a clear understanding of how basic physics simulations work and how easy it is to bring realistic motion to your games. Next, we'll look at a stack of boxes to show how multiple objects can interact via friction and affect each other's movements. In this example, we'll create a series of boxes stacked on top of each other. As the simulation begins, you'll see how gravity pulls the boxes down, how they collide with each other and the ground, and how friction plays a role in their movements. This demonstration will highlight the interactions between multiple objects in a physics simulation. Friction is a force that opposes the relative motion or tendency of such motion of two surfaces in contact. In our simulation, friction affects how the boxes slide against each other and the ground. Higher friction values make the boxes less likely to slide, simulating rougher surfaces, while lower friction values allow more sliding, simulating smoother surfaces. By observing the stack of boxes, you'll get a better understanding of how simulation handles multiple objects and their interactions. You see firsthand how friction influences these interactions, providing a realistic touch to the simulation. You'll learn about collision detection, which determines when and where objects collide, and collision response, which calculates how objects should move after a collision. These concepts are crucial for creating believable physics in games, ensuring that objects behave in a realistic manner when they interact. Time to try some interactive controls. Imagine being able to move objects in your game using the mouse move. We'll add this functionality so you can see how user inputs affect the physics world in real time, making the game more engaging and dynamic. In our first example, we'll demonstrate how you can pick up and move a simple cube using a mouse click. To achieve this, we'll use ray casting, which involves projecting a vector from one point to another, in this case, from the camera to the mouse cursor. When the ray intersects with the cube, we'll determine the pick point, allowing us to move the cube as you drag the mouse. This technique is crucial for creating interactive environments where users can manipulate objects directly, enhancing the immersion and interactivity of your game. Example 2. First-person view with interactive ball shooting. Our second example takes things up a notch. We'll switch to a first-person view where, with a mouse click, we create a ball and apply an impulse in the viewing direction. This means the ball will be launched forward, allowing it to hit and impact other objects, like cubes, in the environment. This example showcases how you can add dynamic and interactive elements to your game, making the player feel like they are truly part of the world. By integrating user inputs with physics simulations, we can create engaging and responsive gameplay experiences. Now, let's explore another fascinating application of physics in games: the raycast vehicle. Imagine creating a vehicle that can drive around in a 3D environment, responding realistically to the terrain and obstacles. To achieve this, we'll use raycasting, a technique we've touched on before. But this time, instead of using it to pick up objects, we'll use it to simulate the vehicle's wheels. Here's how it works. A raycast vehicle uses rays to detect the distance to the ground and calculate the suspension forces on each wheel. Essentially, we're casting invisible rays from the vehicle's wheels down to the surface below. These rays help determine the exact point of contact with the ground and how the suspension should respond. Key components: raycasting for wheel contact. Each wheel casts a ray towards the ground to measure the distance and detect collisions. This information is used to simulate the suspension, ensuring the vehicle reacts to bumps and dips in the terrain. Suspension system. The suspension system absorbs shocks from the terrain, providing a smoother ride. By adjusting the suspension forces based on the raycast results, we can simulate realistic vehicle dynamics. Wheel friction and motor forces. Friction forces are applied to the wheels to simulate traction, allowing the vehicle to accelerate, brake, and turn. Motor forces are used to drive the wheels, propelling the vehicle forward. Vehicle chassis. The main body of the vehicle, or chassis, is connected to the wheels via the suspension system. The chassis responds to the forces generated by the wheels and suspension, moving realistically over the terrain. Benefits: realistic movement. By using raycasting, we ensure that the vehicle's wheels accurately follow the terrain, providing realistic movement and handling. Responsive controls. The vehicle can respond to user inputs like steering, acceleration, and braking in a realistic manner, enhancing the gameplay experience. Dynamic interaction. The vehicle can interact dynamically with various terrains and obstacles, making the environment feel more alive and immersive. In summary, raycast vehicles allow us to create lifelike driving experiences in games. By leveraging the power of raycasting and physics simulation, we can make vehicles that not only look realistic, but feel responsive and engaging to control. Put in the comments if you'd like to know how to transform a standard four-wheel raycast vehicle into a tank. Now, speaking of tanks, I have some exciting news. I have an incredible game featuring realistic tank physics, using the techniques we've covered today. Unfortunately, I don't currently have the rights to publish it, but I have a campaign underway to buy back those rights and make the game available to the public for free. Here's where you come in. I'm aiming to raise $10,000 to make this dream a reality. You can see the progress bar on your screen, showing how close we are to reaching our goal. So, how can you help? I also have developed a mobile app focused on food and fitness exercises, enhanced with AI to provide personalized recommendations. By becoming an early adopter, you can provide valuable feedback and help shape the app. Plus, all purchases and contributions to the app will go directly to the Tank Game Fund. Every bit of support counts, and together we can bring this amazing tank game to life. Check out the links in the description to download the app and join our community of early adopters. Thank you for your support, and let's make this happen. Check out more of my videos about game development and 3D graphics. Thanks for watching.